Okay, so the lecture today is about basic concept around neural networks, specifically also looking at optimization. We'll look at optimization, gradient computation, but also we spent some time with the TAs and over the years try to gather some guidelines on how to optimize these deep models. Originally, we called it multimodal optimization, but a lot of these tricks are true for a large number of applications. So it's not just true for multimodal, but they are definitely very important in multimodal. And so we'll continue to so these are some of the, this is the objective for today. Just a quick reminder from last week. If you remember, not last week, but last lecture, multi-layer feed-forward networks. This is an example with two layers, two hidden layers. If I ask you how many score functions or how many scores you have, in this case is only one score. As you remember, the last layer could have multiple score, multiple neurons. And if you remember, each of these is a little bit like a linear classifier. Each neuron is almost a linear classifier with this activation function that renormalize the output of the classification, the linear classification. And so each of these neurons, for this neuron, you have three inputs. And so you have these parameters. These are called model parameters. And so you have model parameter for one neuron, two neuron, three neuron, four neurons. Concatenate all of them together, that becomes W1. And then you do the same W2 and W3. And so the model parameters, this is what we want to optimize. And we will use the loss function as a measure to know, hey, am I at the right spot? Is it a good place to be for given these W? And you could say at the beginning it's random, these numbers, and then you can compute the loss, and as we'll see, we'll compute the gradient from that. And then make a step, and we'll discuss this in more details. I'll give you a high level, but take a step means you change those parameters. And when you change those parameters, then you can recompute your loss. And that gives you that's one way to see if you're making progress. We'll go more in details in a second. So the core is learning those model parameters. How do we learn those model parameters? As you remember, we have a training set. And a training set in this case will be for a supervised task. So you have X, the input, and Y is the output, the output labels. And we'll suppose for now that this is a fixed training set, that you don't have online learning, for example. And our goal is to learn those weights, both weights and biases together. And as we discussed, you define as part of your model design, we define an architecture, and also at the same time we design also our loss function, or selected a loss function. And if you really don't know which loss function to do, then you could have a bunch of candidates, and we discuss about the possibility of doing model selection as hyperparameters for your model. But we'll discuss that later. But optimization, and I love this analogy. It's a little bit like exploring Switzerland, but folded, blindfolded, and trying to find the highest peak, highest mountain. You could go lowest if you, but let's say you maximize in this case. And so you want to find the highest peak in Switzerland. And so you're walking around, and the only thing you will know is you have this instrument that tells you your altitude, so how high you are, and that's the only thing you do is get that measure. So at any point in time, you can take a step backward, forward, any kind of direction. As you take a step, you get a feeling that you're going down, or you get a feeling you're going up. And that's this idea that you can get your loss at time t not time t, but iteration I, and then your loss at the next iteration in your optimization, and you can see if you're getting better or it's improving, and that's what the gradient is going to help us with. So we want to minimize the loss function. The loss function tells us, given those weights, given that position I'm in, like I'm at one specific position, what is my altitude? How good am I? And how do we do the optimization? There's different approaches, and now these days it has been a strong focus on gradient-based approaches, specifically because a lot of the neural networks or neural architectures have been designed and have been improved to all have some gradient that most of them have analytical gradient that can be computed, and for that reason makes gradient optimization very efficient. We'll discuss more in a second, but the other approach would be to be very exhaustive and try every little place. But as you can imagine, if your space is large, like a space like, let's say, Switzerland, then that it can be very demanding. So so one other approach, and so, is to just search randomly and then refine that search, and to refine that search, that's the key here, is the gradient, and so gradient. I just want to, most of you hopefully had this in either undergrad or some of your grad courses before, but just the gradient is this. It's the direction of the greatest rate of increase of the function, and its magnitude is the slope of the graph in that direction. So here you have a 2D graph. The tangent is at any point in that graph, I can look and say what is the gradient. In the Switzerland example, it is mostly at any point in this is to know the slope of the mountain. That will be the other way to do it. Formally, this is also a derivative of the function. So it's in fact the derivative of your loss function. And in higher dimension, there's different ways of optimizing it. So in multiple dimension, the gradient is the vector of partial derivative. And so this is the, and we'll discuss with an example in a second. But in the Switzerland case, Switzerland, we only had two variables, like am I going X or Y, like it's a 2D, you could see it as a 2D, the action space being going X or Y. And so the gradient will also be two-dimensional. It will be a two-dimensional vector. If you don't have the numerical, the analytical gradient, the way to compute a gradient is just to try it. What is it? You're in Switzerland, you're in the middle, and you have no clue, and you didn't have any kind of map to help you, or local knowledge about the slope. What can you do? You touch, you take a mini step forward, maybe a mini step on the right side, and from that and then see, hey, is it lower or higher? What is my altitude if I take a step forward, a step backward? And so with this, that gives you a nice, that can be one way to get the gradient. But as you expect, this is a very slow process. It's still possible, but it's a slow process. So and can be sensitive on how big of a step you want. You in a perfect world, you want it as small as possible, and sometimes you will need even a hyperparameter. But in most cases, for you moving forward, when you look at neural architectures, a lot of it is because they were designed, or at least one of the great advantage is that a lot of these functions, that activation function and neuron activation function, were designed to be differentiable. And so what it means is that the loss or the local derivatives can be computed, and that's one of the main advantage. So and you will love to have it as an exercise, and you've probably done that in some of your classes. So we don't have to do it. And if you ask what those libraries like PyTorch and all of this are doing underneath, is a lot of this computation for you. And so which one should you use, numerical, analytical? The answer is relatively simple in our case, because we do have analytical. So in the case of neural networks, just want to go a little bit on like how is that gradient computation, okay? And so this is a very simple neural network. You have your input, you have one neurons, and then you have your scoring function, which could be just a normalization of the neuron. And so the gradient is just the derivative. And so in this case is derivative with respect to your input. That's what you want to know. So just a chain rule can be used. If you have many neurons, then it's a multipath chain rule. So it's so at the end you end up one for each of the path that you have. So when you have many neurons, and then it's just become a sum over this. And then when you have also multiple of these of the input, this becomes really important here, because at the end of the day, if I had only one input, I had my gradient is one dimensional, and it's in fact only the size. It was like only one value, the gradient. But if I have many of these x's, in the case of the Switzerland example, I had two of them. I had x and y. I could go in that space, that 2D space of parameters is like so my gradient will have at least two the dimension on this. In this example, we have three of them in this. Okay, so at the end of the day, the gradient is a vector. So there's one value that tells me that loss function, that scores, those scores, that loss function. If I was to make a little change in the direction of x1, will it go up or down? And how much up or down will it be? And so that's the gradient. And the trick here is that there is what makes it efficient, and we'll talk about it in a second. What makes this gradient computation very efficient is that this gradient computation can be done recursively. And that's the beauty of it, is that you have a local gradient, or kind of a local Jacobian, that tells you how much variation between variation between h and x, h given x, like what's the derivative of h given x. And then you can backprop, in fact, from the previous, whatever parent you had from there. Here is very simple. This gives you all of the gradient. But let's look at a more realistic example. Also, although very simple, it's a more realistic example. In this example, it's the same one I've shown earlier, which had like 2 layers of neural networks, 2 hidden layers, and then eventually you get your scores, and then you can compare these scores with the ground truth labels, and that gives you your loss. So it's rare you see a neural network in that sense, but in that way of writing it. But I strongly like this. I like this because everything is there. My parameters, whatever parameters I'm looking for, are there. These are my model parameters. I have my score function, and I have my loss, and then I have my ground truth compared with the scores. And here is just a cross entropy I picked for this example. So the back propagation go into step. Once there's a feed forward pass where you follow the graph. So mostly you have an input here. If you remember, this is an iterative process. So a W has to be initialized to something, and often you just initialize to random, or you may have a warm start where you use another, maybe a clustering or something to help you kickstart things. But usually you could even start with randomly these numbers. So what it means is mostly you got dropped somewhere in Switzerland. Whew. And that's what it means. You got dropped somewhere in Switzerland. And now we need to optimize from there. And so the only thing you will do change is these parameters to move you in the space. So you feed forward. What it means is that you take your training example. Your training examples have X and Y, and you do it for all training example. You run it. You run for each training example with X and Y. Run it through the network. That also will give you a loss. And what I didn't put here, because just simplifying, is that there's a summation over all the training that is done. And so when I'm doing this, I'm doing it as if there was only one X and one Y, but in reality, there's the training. And so you feed forward all of your training data, and then that will allow you to compute these intermediate forward paths. And then you will go and start from the top, and you initialize your gradient as 1, and then you do you compute that local gradient, local Jacobian here, which is between, in this case, will be between L and Z. And then you use the chain rule. So originally my gradient was 1. I go ahead and I multiply by local Jacobian. And then I go on and on and on and on until I get to the final part here. At the end of the day, the vector I will get will be the same dimension as X, as you remember, because that's really what I'm looking for, is like I have X and Y in the case of Switzerland. Oh, sorry, I use X and Y. It's confusing. Sorry, I meant you have X1 and X2 here, where the two direction I could go in my Switzerland space, but I need to compute this efficiently with this. Okay, so this is backpropagation. If you want to know more, let us know. We can give you plenty of pointers on that for this. But what I wanted to emphasize is that the beauty of these neural architectures is that although it's very complex, like these neurons could be very simple, like a linear activation function, or themselves could be a very complex still. You could have a full transformer, like for people who know about transformers or self-attention module or CNN. These could be a full, very complex unit. But as long as you already have analytically the gradient, the analytical gradient between the input and output of this module, this is all that I need. As long as I can compute that local Jacobian, like what is locally this derivative, this is all that I need to be very efficient. I may not even need to go inside it. In most cases, and the example I will have in class, I will have these units relatively simple. There will be neurons, and you could go and write it by hand. What's really nice with these the libraries like PyTorch and others is that they create those computational units for you, and they already have internally like the knowledge of the gradients, and then you just create a bunch of layers. But what is happening, what is the hardest for a lot of this, is how to compute the gradients efficiently. And so I talk about a sigmoid, that's a simple one, but even a sigmoid unit really have inside it many different steps. Like there's divide, there's adding, exponent. So all of this is but the nice thing is, as long as these components are differentiable, then the full architecture with all of these differentiable will also be differentiable. And so that's the beauty of neural networks. So this was a summary and a quick view of that. Gradient descent is the idea that now I know how to compute my gradient analytically with neural networks. So at any point in time when I'm in Switzerland, I will be able to know where's the slope of it. And so I have that key thing, gradient now. That's a big important. I have two tools for me. One is my loss function. At any point in time in Switzerland, I can look at the altitude. That's my loss function. The other tool I have is the gradient. At any point in time, I can go and look and find the slope of the mountains. These are the two tools I will be using during my optimization. And the simplest one is in fact gradient descent. What it is at any point in time, I look at the slope and make a decision to go where the slope is going. Like, so if the slope is going down more toward x2 or more toward x1, I will take a step meaning I take an incremental step, and that's in fact a hyperparameter of the optimization of how big a step I should take. But let's say for now, I could take a step of one being 1 time the gradient, just for simplicity for now. We'll talk about how big of a step we should take. That's a big important aspect of that. But there are, in fact, courses on optimization, and these are very interesting. I highly suggest to take the time to take a full class on optimization. I will just give you a hint about these different approaches. Is that instead of taking the gradient, you could take the derivative of the derivative. So gradient is a derivative of the loss, and then you could take a derivative of that. Most likely you will do a numerical derivative in this case, but you may be lucky and you can easily have the analytical gradient of the second one. But the Hessian, which is that second derivative, is very interesting. It's kind of the acceleration of the velocity in this case. And that can give you or guide you of how big of a step you should take. And so there's many different one, BFGS, which is, if you wonder why it's called BFGS, it is the last name of, I think, all the authors. And LBFGS, just an extension of that. So instead of always taking a first step, then you could go and kind of approximate the Hessian, and then that will hopefully give you better better knowledge. Now, because in a sense, you may end up taking less steps by doing something like quasi-Newton or Newton approach, but they're computationally more demanding. And so there's a trade-off, and so neural network often will just go and directly go with gradient descent in this case. So the parameters used, and so in reality, you would like to decide like how big my parameters. Here I use theta. It's just a notation change. I personally prefer theta over W, but this could be W. So WT and WT plus 1. I use T here. Sometimes also I prefer just to use I, because T is not because time like a sequence of time, but it's time in the sense of optimization time, like optimization iterations. And so the basic gradient descent just say, hey, this is my W at time T. I want to compute my new W. And what I will do is use my gradient and just take a step in that direction. And how big of a step is what we will often call learning rate. And so the learning rate will be very important. It's like, how big of a step should I take? You could get like a constant one, always the same. In practice, you will vary this. And so you will have a learning rate and maybe a decay of this. So you have an initial learning rate. And then you can have also kind of a decay learning rate, which is linear until iteration. So this is there's a lot of these tricks you can do of like, so you could just decay this and with an increase. And so these are some of the approaches. In practice now these days, I will say maybe, I don't know how many years, maybe 5 years ago, a lot of this was still using these. Now these days we have some that are working with extension, which will do approximation, more accurate approximation of this. I just listed some of them here. and there are new ones almost every year also coming up. So I don't want to go in details on this vanilla gradient descent. What I want to say is that also one of the challenge, and this is something more of a design thing, is that you have a data set, and if you remember when I said you compute your gradient, one of the first steps is you have x and y, and then I said, hey, for your whole data set, you want to be able to take for the whole data set, run feed forward, and then compute your gradient with that information. So this will be true. And back in the days when the data sets were small, it was not of an issue. And then you have a spectrum. So one is you use all of your data every time. And sometimes it's needed, like a lot of the Newton approaches requires almost sometimes to have all of your data to work well. But on the extreme case is to pick only one sample. It's called a stochastic gradient, where you will just pick one sample, compute the gradient, take a step, and go pick another random sample, make a step, compute a gradient, make a step in optimization. As you can expect, there's somewhere in the middle, and so batch processing will be, and the hope there is that you have enough information there that's representative of your whole data set, but is also computationally more efficient. So, okay, and we will call this an epoch or an iteration when you manage to go through all of your data. So a batch approach will usually, what it will end up doing is that you will in fact go through all of your batches. So if you take all your data and slice, bin and put it in bins or batches, then an epoch is over all of this. So I want to emphasize a little concept where you hear sometimes me saying this is convex versus non-convex. Convex will be wonderful if life were, not life was convex, but maybe if life was convex too, but if your function was convex, it would be great. What it means is that wherever you start, you will always find that local minima, or if it's maximization, local maxima. But in most cases, Switzerland included, Switzerland is a non-convex, I don't know if you can say a non-convex country, but it's definitely a non-convex case, because there are local minima, or in the case of Switzerland, a lot of local maxima. So that is in itself a big challenge, and there's a lot of very interesting work that has been done. Some of it is very well theoretically grounded. Some of it is also just guidelines that you learn through trial and through sharing experience with colleagues. And so, but when you have those local minima, you have different versions of that. But one of the big challenges when you have a local minima, you have a few of these, but one of them will be, for example, is to just clearly just getting stuck there, like thinking that the local minima is the global minima. Another version of it is that if your steps is too large, if you took too big of a step, then you will end up oscillating back and forth in that local minima. And if you have flat, then they are very close to flat or flat, then the gradient, it will be very hard to get out of this, because you suddenly, the steps will just be, the gradient will be a lot less informative there. And then this is why you can think of being adaptive in your, because it will help you to go out of this. And so there's different, you can do it empirically to show the difference of a good learning rate with a bad learning rate. When you do train a model, always plot your loss over iterations. It's like, this is 101 to do that. Another trick that I forgot if I put it in the slides later, but always look at your training loss, how much, and the general rule of thumb is that you want to be sure that your model is able to overfit, to train, to work on your training data. And then you could look at your validation set and see if it generalizes. I think I have some slides about it later, but the general rule of thumb is always look at the loss, training loss. You want your training loss to go down. If it does not, then there's two things. I mean, one is the model may not be either enough flexible, or there's maybe a need for a better initialization, or in this case will be a better learning rate. So these are important to do. In reality, learning rates never look like the left. It looks a lot more like this. And don't worry, that's a more typical learning rate. But you want sorry, I said typical learning rate. This is a loss. This is a typical loss depiction. So and so here the x-axis will be iteration, and so here it will be the loss. Okay, practical guidelines. Let me give you a few of these. I will go relatively quickly over that. We put a lot of information in this, but so let me go through them. If you have questions, we're really happy to answer that. Because we have this special event, team matching event, then we'll shorten a little bit this practical guideline. And next week, we're starting with the good stuff. We're going to do visual representation, language representations. We'll also start the week after that with the multimodal representation. So all the good stuff is coming in the coming week. But these are important. I mean, most of you probably took a class maybe in machine learning. All of you probably took a class in machine learning, but some of you also probably took in deep learning. So you may know some of these tricks. I talked about it already about adaptive learning rate, and I gave examples of that. This is just an animation that showed the advantages of these, because sometimes you will overshoot or undershoot these kind of situation, and so it can be very challenging here. You can see if you overshoot, you can clearly get out of this. I also told you about the challenge of local minimum or local maximum. I want to discuss the saddle point. The saddle point is very challenging, deep learning, because there's many of these minima, and many, not all of them, are actually almost as good as the global due to parameter permutation. So lots and lot of saddles in many deep learning model. And so saddle is like this place where it's not just a valley, it also goes down. And so if in this case you were trying to go up, you could easily get and fall almost out of the cliff. So just some approaches to detect the saddles. You can calculate the Hessian. We talk about it when we talk about the Newton approaches. And so this is one way to look at this and be able to help with these saddle point. I'm not giving as much in this kind of on purpose, because now these days there are a lot of these that a lot of these tricks have been included in these different libraries. So you can handle a lot of them from that. One also to be aware is that if you look, it's not always the fault of the learning rate or the momentum. It's sometimes it's also just the data or the model, the data itself. And so it's always good to go ahead, and you want to be sure, as a first step, you want to be sure that you are able to overfit on the training data. I mean, this is step number one. You want to be sure that you overfit on your data. So if you at least manage to overfit to the data, that means that the model has enough flexibility to get there. Now you may need after that to do some what will regularization, which I'll talk in a second, to go from something that's like maybe over complex to something that's a little bit more simpler. But the first step first is like, let's go ahead and just be sure you can fit to this, even if you're kind of having a lot more complexity to your model than needed. At least you know there's a path to success. If you don't have this, then revisit a lot the momentum and the different learning parameters. There's the problem of bias and variance. Simple models are unlikely to find a solution to a hard problem, and thus probability of finding the right model is low. So that's one of the issue, and like the linear classifier will be an extreme version. And complex model on the other side find many solutions to the problem, but they may not generalize as well. And so that's one of the problem, and neural networks are there. And so that's why the key second aspect to that is regularization. Regularization, we discussed very quickly last lecture. Let me give you a little bit more intuition. It's easier to think about it, at least for me, visually. So regularization is the idea, and like simple regularization, like L2 regularization. What will help you is that although you may not see every example, you may want to be able to generalize to new cases. And L2 generalization is nice in that sense, is that it will help that even if you don't see some example, that you will hopefully be able to generalize better. The L1 is nice because it allow you to, or force you to be zero for some of the parameters, and that brings us some sparsity. And there's a lot of other regularization with this. So the most typical L1 regularization, if you were to take this linear classifier and put L1 regularization, this is mostly lasso. And if you do L2, this is mostly what's also called ridge. And if you put the two together, it's called elastic net. You may have heard that. Elastic net is a really good contender. I told you earlier, do K nearest neighbor. I will say one other one that's really good is just a simple elastic net on your problem, just to see like very simple model. What does it pick up? Does it pick up anything? You'll be surprised the number of times that if you have very good features, very good input features, a linear or very simple model could be really good as well. So it's always healthy to have those like nearest neighbor and simple like the elastic net to go with this. So structural regularization, lots of model can learn everything and go for the simple one. And so that's a general rule of thumb. And so the way of regularizing, there's different ways of regularizing. The one that people always think about will be about adding kind of a term like I said, L1 or L2, or dropout, which is also another type of regularization, which we'll talk in a second about. But the other way of kind of model-based kind of, you could say, regularizing is just to go with simple model first and slowly go more and more complex. So one, you go complex and then put regularization. The other, go simple model and slowly building that. So that will be another approach, and I strongly suggest that as well. So I want to talk about co-adaptation, and that also gives you an intuition about dropout, why this dropout regularization is also quite important. And so there is this issue in many neural networks. Multi-layer perceptron will often have, if you're not careful, is that there's a few things that can happen. A neuron learn something that is not useful, and that can happen. I mean, if you start randomly initializing thing, it's possible that neurons can learn something that is not useful. The issue with that, if it was just like, hey, some neurons don't, then the other neuron will learn to fight this useless neuron. So and so you may end up with one neuron and the other neuron to kind of compensate that wrong or neuron, and then only maybe some subset of that end up using really the right learning, the right thing. And so there's different approaches, but one that's been very nicely is to just drop, simply multiply the output of a hidden layer with a mask of 0, which is kind of equivalent to dropping some of these neurons. And this is during training, you will do that. And so during training, you will randomly, and there's a hyperparameter here, which is how many of these you will drop. And you could see it as just multiplying with Bernoulli distribution. So the dropout, the forward step is you multiply with the Bernoulli distribution. That's, if you remember, in the back propagation, the first step is forward, and so you will randomly, and then the backwards just calculate the gradient the same as before. And so the forward is which ones works better. The backward, some neurons are out of the network, so how does this work? All good? No. So you need to also do a small adjustment. I mean, this is more of a little kind of implementation details just to know, but in the back preparation, you need to change a little bit the reweighting of that, because you suddenly don't have all of the neurons that were activated. So dropout, stop co-adaptation, and learn kind of an ensemble. You could see it as learning kind of an ensemble, because some of it, and so it will force neurons that were like useless to not be useless, because maybe this neuron originally was the really good one that was doing all the job, but it got turned off. So now the other neurons need to also be working as well. And there's some extension of that. And so you say Gaussian dropout, instead of multiplying by Bernoulli, you multiply by Gaussian with mean 1. You can also allow skip connection to happen. I invite you to look at these for that. So the last part I want to bring is maybe a little bit more specific to multimodal optimization, although as you can expect, these also come in some other optimization problem. But in multimodal, some of the biggest challenge is the data is from different sources. And so in many cases, let's say the simplest one that we will gave an example earlier was in the previous lectures was for images and captions. And if you remember, we had the red car or blue car. And so you have the image of a blue car and you have the caption of a blue car. And so when you're learning to process these and when you model these, you often, let's say for the language, you may have a recurrent neural network, or these days you may use more of a transformer or self-attention model. But let's say for simplicity, let's use a recurrent neural network. And for the image, you may have a CNN, or both of these we'll talk about more next week. But in itself, both are what we call computation units, because that's a big computation unit, a CNN, and a big computation, an STM. And they have, each of them can have different ways to be trained, and not be different ways to, they're all trained to gradient, but the gradient, if you do it from scratch, there's some issues that could come out. For example, maybe one of the two tasks is a lot harder to train than the other, and maybe most of the gradient goes that way, making it harder for the other to train. There's a lot of these issues that will happen in multimodal. And so CNNs, some of the example where you have these, I talked already, CNN work well with high decay learning rate. This is just something, some of the rule of thumb that we want to share with you. What we mean also with this is that there may be not the same learning rate for each of these modules. You may want to, and I'm about to talk about pre-training as a place to go. So one of the key aspects in multimodal that you will hear, and now you hear it a lot more. Pre-training has been very popular in computer vision since 2011, but in natural language processing for the last 3-ish years, a little bit more, maybe a little more or less, pre-training also became very popular in NLP, to the point now you probably hear in the news about GPT, pre-training of GPT from OpenAI and others. The idea is that these different modules can be hard to train all together. And so the idea is to pre-train that. So let's say my task is sentiment. My sentiment meaning you're listening, you're watching me, and you're also looking at my words. And so you have language and images. And so you want to train detector for sentiment. So it's going to be a CNN, LSTM, and maybe a simple MLP. And then that's what you want to train. The idea of pre-training is the idea of, there's two types of pre-training. Here, what I showed here is pre-training with supervised tasks. So you will use another task, maybe just also sentiment, but just on images, which could be just emotion recognition, like positive versus negative emotion recognition. And on language, you could imagine pre-training with a task, also maybe sentiment analysis. There's also other type of pre-training, which we'll discuss more, which try to do either you could call them unsupervised or self-supervised, where you don't have the label, but find a way to train the CNN even if you don't have label. In the case of image, it could be because it's like the jigsaw puzzle that's called, is like you take all your image and I maybe hide part of the image and try to generate it, the rest of that image, or you reshuffle the image parts and try to have the CNN solve which part is where. This is examples. We'll discuss more later. In language, what's very popular with self-attention, where you hide a part of the sentence, that's one of the type, and try to have the rest of the sentence also be able to predict that missing information. This is kind of a extension of what I talked about already when we talk about word2vec of distributional hypothesis, which says the context of a word is very predictive of the meaning of the word. So anyway, what I want to say here is that there's a lot of interest in pre-training. So the weight model parameter of the CNN will be first learned here on the for the CNN first, and then also separately on the LSTM, and eventually you will put them together, and then you can go two ways at that point. You could say, hey, I pre-trained CNN, I pre-trained my LSTM, then I will not change anymore the CNN and LSTM, and I will only learn MLP. Or you could say, I will at the time of this full training to go ahead and do ML fine-tuning of the parameters as well. And that is very important in multimodal and other places.